Hello and welcome back to my physics online video lecture supplement series. In today's video, I wanted to sort of open the mailbag and answer a question which I received actually both by email and in person after class by separate people. So I guess there is some interest in this particular question. It's basically a question of geometry. The question basically has to do with the work energy theorem and really with how much work is done to a block that slides down a ramp. So this is basically block on ramp with friction, and was sort of a why is it that this is what the equations look like. So let's pull up the block on a ramp. Here is our block on a ramp. The ramp is at some angle theta with respect to the horizontal. The block slides some distance delta x along the ramp, and we'll go ahead and construct our axes so that delta x is along the ramp and delta y is perpendicular to the ramp. And the question is, how much work is done on the block? So work done on block. Now, there is some coefficient of friction, mu sub k, and it is not 0. The total work done on the block should be given by the sum of the forces dotted with the vector displacement, delta r, which in this case would be basically delta x, if you will. And we can find this sum dot product by basically taking each individual force and dotting it with the displacement. So really that means that the work done is going to be gravity dotted with the displacement plus the normal force dotted with the displacement plus the force of friction dotted with the displacement. So now let's look at each of these things. So the displacement is entirely in the x direction. If we were to draw out gravity and normal force, we would see that the normal force is entirely in the y direction. Friction is entirely in the x direction, and gravity is pulling basically downwards in neither the x nor the y direction. Not to scale, of course. All right, so this means that this term right here is basically going to go away. And so we can look at gravity and we can look at friction. So let's do friction first. Friction is going to be given by the normal force times the coefficient of kinetic friction. So that means that the work done by friction should be the kinetic friction times the normal force, which basically in this case is m times g times the cosine of theta. And that is going to be times the displacement delta x. Now, why is it cosine of theta in this case? Well, basically, for this block, we need gravity and the normal force in the y direction to balance. So if I were to draw this vector for gravity into two components, there would be a y component and there would be an x component. And in the y direction, the sum of all forces should be 0. So that implies that the gravitational force, Fgy, and the normal force, Fn, need to balance to 0. And actually, it's a matter of simple geometry here. See, this is the gravitational force, and it's perpendicular to this horizontal line. These two must be perpendicular. This is angle theta. The this angle FGY has to be perpendicular with this ramp. That is, in fact, what it means to be in the y direction. This angle right here, therefore, must be 90 minus theta. And since this whole thing is 90, that means that this angle right here is also theta. And so FGY is going to be given by FG times the cosine of theta. And so that's mg cosine theta, and that's where this term right here comes from. So that's how you find the work done by friction. Now, the bigger question comes in when we try to find the work done by gravity. To see how we get the work done by gravity, I've redrawn this diagram, again looking at Fg and at Fn and so on. We're ignoring friction here because we just want to know how much work is done by gravity. And that should be, work done by gravity should be the force of gravity as a vector dotted with the displacement as a vector. So the dot product says that this angle right here is phi. And so the work done by gravity should be the magnitude of the gravity vector, which is m times g, because the force of gravity is m times g. The delta r, we're using basically a delta x, and then that should be times the cosine of the angle in between the displacement vector and the force vector, which would be, I'm labeling it phi as opposed to theta. Theta is giving this angle, phi is giving this angle. This is a 90-degree angle. So notice that phi is actually equal to 90 degrees minus theta. So that means that the cosine of phi is equal to the cosine of 90 degrees minus theta. And there's an identity for this. So at this point, it may be helpful to pull out our handy-dandy chart of trig identities. And I look down here and I notice this identity here, cosine of 90 minus x is equal to sine of x. And really, you can get that from using these other identities. Cosine of x minus y is equal to cosine x cosine y plus sine x sine y. So x minus y, if x is 90 degrees and y is theta, you'd have cosine of 90, which is 0. And then you'd have sine of 90, which is 1 times sine of theta. So what this basically is telling us is, either way you slice it, this function here, this cosine phi is cosine 90 minus theta, is basically telling us that the cosine of phi is equivalent to the sine of theta. And we can actually see that again because remember that cosine is the adjacent divided by the hypotenuse. So the cosine of phi would be this side divided by this side. And sine is opposite over hypotenuse. So sine of this guy is this guy divided by this guy. So it's the same thing. Therefore, we can write that the work done by gravity is going to be m times g times delta x times the sine of theta, as opposed to the work done by friction, which was mu sub k m g delta x times the cosine of theta. And this was basically the question that was asked both in person and by email from a couple different students. Why is it that one is sine and one is cosine? Well, I guess now you know. But to sort of further this answer, let's look at this term here, the gravity term. If we take delta x and we multiply it by the sine of theta, or by the cosine of phi, either way, that basically, the sine of theta is going to be hypotenuse in the denominator and opposite in the numerator, well, the opposite side would be this side right here, which I'm going to call delta H for change in height. So this means that if you have delta x times the sine of theta, you should get whatever the opposite side is, which is the change in height. And so this work done by gravity, therefore, would be m times g times this whole term together makes change in height. And that's the familiar equation that we derived elsewhere in class by taking a falling object. So I hope that this helps clarify the question that you've all asked, and thanks for watching.